Over to you, Colin.
Right, thank you, Vicky. I wanted to start just by holding this up. I hope everybody can see that. This is the title of the book that goes with the lecture. It's the Anthropocene as a Geological Time Unit, and it was published by Cambridge University Press in 2019. So if you want lots of detailed information about the geology and geochemistry behind the Anthropocene, why it's being discussed as a geological time unit, that book is the place to start. So what I'm going to do now is talk about, is introduce you to these slides. So the title here, okay, so the Anthropocene, a new geological epoch driven by human impact. So here we are. There is a beautiful picture from NASA of Earth from space. Actually, you can see it's not so much Earth, it's much more ocean. We are really the blue planet because 72% of our surface is ocean. And you can see that from the picture on the right. This is a photograph taken by the Voyager 1 space probe when it was 6 billion kilometers away from Earth, heading out of the solar system. And Carl Sagan, who was one of the people who got the instrumentation onto Voyager 1, asked them to turn the camera around and photograph Earth back from where they were. And there it is, a pale blue dot. And he's used that symbol of a pale blue dot within that red circle to describe Earth. And it helps to understand the message that we have one planet, planet A. We don't have a planet B, so we don't really want to mess up planet A any more than we can possibly do. So moving on then, there we go, next one. Here we are introducing the Anthropocene. On the left is the present ratified geological scheme. So you can see on the left, there's the Phanerozoic eon, there's the Cenozoic era, there's the Quaternary period, and then we get into the Holocene and Pleistocene epoch, and they are divided into smaller parts. Now you may possibly not be aware, because this is quite recent, that the Holocene itself is now divided into three: the Megalohalian, the North Grippian, and the Greenlandian. And there on the right-hand side of that left-hand diagram, you can see the ages of the boundaries. Like the boundary of the Megalayan is 4,250 years before 2K. So on the right-hand side is what we want to do. We want to add an additional stage. This would be an epoch stage, the Anthropocene, bringing the Holocene to an end. And the date that we are discussing for this, as you see on the right-hand side, there is the mid-20th century. And I'll explain why that is as we go along. But just to give you some context, the first cities arose 10,000 years ago. That was in the Greenlandian, just after the beginning of the Holocene time. The last glacier maximum was 20,000 years ago, and that's back in stage 4, the upper or late Pleistocene. And then the first Homo sapiens were running around on the planet 300,000 years before present, and that would have been in the middle Pleistocene. So what we're looking for, you see down the right-hand side of this stratigraphic box there, these little symbols that look like golden nails. These are actually representations of the golden spike, which is meant to be pounded in at the boundary between any geological stage and its follower. So these are called global boundary stratotype section and point markers. And we are currently working on finding the markers that will mark the boundary, the lower boundary of the Anthropocene, so that we can present the case from our Anthropocene working group through to the Subcommission on Quaternary Stratigraphy, and they will then present it, if they're happy with it, to the International Commission on Stratigraphy, which is the body that has to actually finally validate this as a new geological unit. So the Anthropocene, yes, we humans have become a geological force on the surface of the planet. We are making so many changes. We are in fact creating we believe we're creating a new geological epoch. And there are lots of geological deposits forming now that include a fingerprint that's distinct from that of the current Holocene epoch, which we have been living in. And those fingerprints have a high potential to remain in the geological record for future geologists to uncover. Now, this is not the first detectable anthropogenic change, because of course, even back in the Paleolithic Stone Age, man was dropping bits of hand axe and so on around. So that we've seen anthropogenic influences begin and then grow over time, but it became recognizable worldwide in 1950 with massive changes in our impacts. So what we can see from these impacts is that, in effect, Earth has experienced a rupture in its functioning. We are all well aware of the fact that human well-being has grown over the past 200 years, but we're also aware, I think, that the planet has become much warmer and more polluted and less biodiverse. And so there is a question as to what the new Anthropocene will look like as we go forward. And that is, will it be adequate to maintain the life support system that we've come to rely on? So the guy who started all this off is here. This is Paul Krutzen, a Dutch atmospheric chemist. He was one of the people that finally figured out how the ozone hole came to be an ozone hole. So he's very famous for that. And he was at a meeting in the year 2000 to talk about the changes that were going on in the latter part of the Holocene. And he interrupted his own discourse to say, no, we're not in the Holocene anymore. We're in something different. And he cast his mind around and came up with this idea that we're in the Anthropocene, human time. And that seems to have stuck, although at the time, he thought it might have begun in the Industrial Revolution. So let's look at some geology now. This is the profile back on the left of the top diagram. You see 0, that's today. That's on the right-hand side. On the left, you see 3.5, that's 3.5 million years ago. And up the left-hand scale is carbon dioxide in parts per million. And what we see is that the parts per million of carbon dioxide in the mid-Pliocene, 3 to 3.5 million years ago, they were up around about between 350 and 450 parts per million, perhaps averaging around about 400 parts per million. And if you go across to the right, you see that the carbon dioxide declined out of the warm Pliocene down into the cold of the Ice Age, which in effect, the Pleistocene time began about 2.6, 2.7 million years ago. And you can see carbon dioxide was pretty low as we entered the Pleistocene, and it stayed low. And on the right-hand side, you can see the black ups and downs. Those are from the longest ice core in Antarctica, representing 800,000 years of time. And the ups and downs represent the Milankovitch cycles of insolation. And what you can see at the very far right is that the carbon dioxide has now risen to around about 410 parts per million, which is, as you see from the dashed line with the red arrow at the end going off to the left, is about the same as it was in Pliocene time. So there is a concern that with this degree of rise in carbon dioxide, we may well be heading for temperatures very similar to what they were in the Pliocene. Now, the bottom diagram is the simulated temperature from models up the left-hand scale and the reconstructed temperature from paleoclimatic data on the lower scale. So what we see is that the coldest temperatures down at the bottom left were in the last glacial maximum. And then as we slide up this line, we get to temperatures typical of the mid-Holocene. So that's 0 on the temperature scale. And the last interglacial, that's the Eemian, where they were slightly warmer than that, about 1 degree. And moving further up, we get to the mid-Pliocene, when we've just looked in the upper diagram at 410 for an average amount of carbon dioxide. And if you continue going up that line, you'd eventually get to the Eocene, when temperatures were very much higher than they are today. We also know that carbon dioxide was very much higher in the early Eocene, so roundabouts between 700 and 1,000 parts per million. So this is the kind of thing that represents a worry for people interested in our future climate. So let's look in a bit more detail then. In this graph at the left, what we're looking at is the past 450,000 years, again from an Antarctic ice core. And we're looking at two things here which represent changes to the carbon cycle. These are carbon dioxide and methane. And what we're looking at is in red at the bottom, going from today back to 450, is the fluctuations in methane due to the Milankovitch cycles. So when there were warm periods, like 150,000 years ago, you got lots of methane. When there were cold periods just before 150,000 years ago, got rather little. And the methane average, the maximum methane average, if you read across to the left-hand red scale, was round about 600 parts per billion of methane. So it's rather a small signal. Let's look at the carbon dioxide, which is blue on the right-hand scale, and we can see it underwent those same fluctuations, paralleling the changes in temperature. And so back in the Eemian, that's 150,000 years ago, roughly, we had carbon dioxide levels that were about 280 parts per million. And in each of the preceding large interglacials at 250, 340, and 400,000 years ago, we had about the same. So the maximum amount of warming in the Milankovitch cycles corresponds to a parts per million of carbon dioxide of 280. And during the very cold periods, like around about 20,000 years ago, we had only 180. So the fluctuation, the natural envelope for carbon dioxide through the past 400,000 years was between 180 and 280 parts per million. And that goes along with the changes in temperature. So where were we in the year 2000? We were up where these two stars are on both of these axes. So we were up about 380 parts per million carbon dioxide, and we were up at about 1,500 parts per billion of methane. And by 2019, we were up at almost 1,900 parts per billion methane, and we were up to about 411 parts per million carbon dioxide. So these greenhouse gases have increased significantly with time. The importance of the methane is, even though it's in small amounts, parts per billion, it's 28 times more powerful as a greenhouse gas than carbon dioxide. So it still is a very important feature of our climate system. Now, on the right, you see this sort of funny little graph expressed in blue. And what this is showing us is the routes to three possible futures, A, B, and C. So if you imagine that we see, and where it says past, we're seeing our carbon dioxide and temperature increase up to where it says inflection point, and then change in one way. Either we will continue warming, and eventually that may flatten out, that's curve A, or we will do some hard work to stop it getting quite so high, and we'll follow path B with our temperature and carbon dioxide, or we will make strenuous efforts and somehow manage to get down on path C with both temperature and carbon dioxide. So that's the background for the sort of work that the UK is going to be overseeing in November in Glasgow when it hosts the next meeting of the Conference of the Parties to the UN Framework Convention on Climate Change. So how do we know what the CO2 levels were in the not too distant past? For that, we turn to ice cores. Now, on the right-hand side, you see this hand in a glove holding the chopped off top edge of an ice core. Now, ice cores are solid. We drill with a hollow drilling bit. So what we're recovering is a solid rod of ice that comes up through the hole in the middle of the drill bit. And we retrieve them in about meter-long sections and then send them off for analysis in the lab. But when you take a slice of this off the top and you hold it up to the light, what you see are all these little nodules. Each of those is a bubble of fossil air. And so we can melt that ice in the lab and trap that fossil air and analyze its composition. And when we do so, as you see in the graph on the left, here we're going from the year, it's actually 2005 on the right, down to about AD 900 on the left. And up the left-hand side is the carbon dioxide scale from 260 to 400 parts per million. And what we see is that all of these different ice cores represented by the different symbols had right up till about 1769 had 280 parts per million in them, which is exactly the same number that we had in the peak of the Eemian and the previous large interglacials of the Pleistocene. But from 1769, we see this increase starting slowly and then speeding up. And so all of the red crosses and so on are from these various ice cores, and they map on to the blue line. Now, the blue line comes from our modern measurements in air, which we started making in detail in 1957. And they take us up to that 411 parts per million, where we're now at. And so what we know from this is that in recent years, we have been changing the carbon concentration of the atmosphere by we're putting 20 parts per million of carbon dioxide every decade, whereas in glacial times, this whole previous 400,000 years to 800,000 years, nature never changed it faster than 20 parts per million in 1,000 years. So we are doing this 100 times faster than nature, and we're now at 410. So that's the basic underpinning. Our emissions are transforming the atmosphere. And this is, so everything you see in the blue part represents, we're living in a different time with a different atmosphere from anything that went before. What was significant about 1769, some of you may remember that this is when James Watt patented his steam engine and everybody wanted one, and so masses of coal started to be burnt. So let's look at what happened in the Eemian when the average temperature in the Eemian was about a degree warmer than it was in the Holocene. Okay, so here at the top in black is the sea level represented from sediment core analyses in the Red Sea. This is the work of Eelco Rolling in a paper published in 2019. So what we see is that 0 represents today's sea level. So starting around about 130, that would be 120, 5, 6, 7, 8, 120, almost 130,000 years ago, the sea level started rising. It went through a dip and then got up to, if you read across the scale, to 15 meters above today's level. And then it declined down to about today's level and rose again to around about 5 meters. So for this whole period of 5,000 years, 5 or 6,000 years, we had sea levels that were bouncing around between plus 5 meters and plus 15 meters. Where did that come from? Well, Rolling's analysis suggests that from the green line down, this is the black curve is in the lower graph. The black curve has been broken out into an Antarctic contribution and a Greenland contribution. So melting ice in Antarctica is represented by the green line. So you can see that that follows the black line fairly closely. And then, in the early period, from about 126,000 to 130,000, Greenland wasn't actually melting very much at all. The melting in Greenland started around about 126,000 years ago, and the blue curve shows you how that then rose to probably about 6 meters, reading off from the left-hand scale. And it's the blue and the green added together from the two ice caps at the different ends of the two ice sheets at the different ends of the planet that gave us the black curve. So we can look in more detail at the climate history of the past 2,000 years to put the Anthropocene in context. And this graph comes from the latest report of the Intergovernmental Panel on Climate Change published in August 2021. On the left-hand side, we see the past 2,000 years of climate going from 2020 right the way back to the year 1. And what we see in the zero line is the average temperature from 1850 to 1900. So that's what we call generally our pre-industrial temperature. And you can see back in the medieval era, the medieval period down there, the temperatures were about 1.1 to 0.2 degrees above that 1850 to 1900 temperature. And they declined down to about 0.2 to 0.3 degrees below that 1850 to 1900 temperatures between 16, 1700. That is the so-called Little Ice Age. And then from about 1850 onwards, you see things really start to change quite radically. The temperatures rise and they go on rising and rising and rising. The blue colors represent reconstructed temperatures from geological data, and the black represents actually observed temperatures. So what we're going to do is move to the right-hand graph now, which is an expansion of that bit on the lower scale at the left, 1850 to 2020. So here we are moving on the right-hand side from 1850 to 2020. And we see that for much of this period, there wasn't a great deal of change in temperature. Once again, the zero line represents 1850 to 1900. So if you go and look at the left-hand side of that right-hand graph, you see the temperatures in black, which represent observed, are hovering up and down for that 1850 to 1900 period around the zero line. And then things start to change. We get slight increase from about 1900 climbing up towards the period around about just 1940, flattening around about 1950, and then a really sharp increase from about 1960 onwards. A sharp increase in the black wiggly line. The wiggles represent the annual change. So the observed line really takes off from, just shortly after 1950. And we can simulate that, well, first of all, we can divide that signal into two parts. What was the natural variation due to solar change and volcanic change? And when we look at that signal and we put that through a numerical modeling system, we come up with this blue line, which is more or less horizontal with some wiggles. So that's the variation that we should have expected in our climate if we had natural forcing only. We do the modeling now, we add in the carbon dioxide and methane and other gases like nitrous oxide, and that gives us the red line that runs through with the black data. So the total observed signal, the black line, represents the simulated human and natural change that we should expect, and that ties in very well with what we've actually observed. So something happened around about 1950. It's a real significant boundary in Earth's climate history. And we can see that in lots of different data sets. I'm just going to very quickly introduce you to these. The top one on the left is the land surface air temperature. Again, you see from about 1950 increase. The next one is the sea surface temperature. And again, you see some wiggles up and down, but you can see from the latter part, since about 1950, we've seen this fairly steady rise in temperature. Similarly, marine air temperature from about 1950 has been increasing. Sea level, there are 6 different data sets, all showing the same steady, more or less steady increase. In fact, a slight increase in rate of increase. The bottom diagram on the left is the snow in the Northern Hemisphere, and you put an average line through that, and you can see the snow cover has been decreasing, which is what you'd expect if the climate was warming. On the very right-hand side, you can see at the top, tropospheric temperature increasing. The second one is ocean heat content increasing, then specific humidity. Why would that increase? Well, it turns out that humidity increases by 7% for every 1 degree of global heating. You get more moisture in the air, which explains why you get floods associated with global warming. Then we see the next one down is the Arctic sea ice extent. I guess everybody knows that the Arctic sea ice extent has been decreasing. And then in the bottom one, it's the total glacier mass balances from, that's from Greenland, Antarctica, and mountain ice. So all of these things are different data sets that completely hang together. And here's a different one which shows much the same thing. Warming up the left-hand side, and the cumulative carbon emissions along the bottom. 0 is the year 2017. So up until 2017, up by 2017, we had emitted 400 gigatons of carbon, 400 gigatons of carbon. And so that means CO2. And the black line shows you the way that temperature increased. So the temperature increase is following very nicely the pattern of release of carbon from burning fossil fuels. And the blue line shows you a projection. If we carried on burning fossil fuel for 200 gigatons worth, 400 gigatons worth of emissions, and so on, these are the temperatures we could expect to get. These are temperatures relative to the average for 1850 to 1900. Okay, so what's actually going on? Well, to help us understand that, we look at this graph, which goes from 1850 on the left to 2010 on the right. And what we're seeing is the burning of coal, which started slow and hadn't built up fantastically by 1950, slightly increased and then continued to increase after 1950. Oil in green really took off after 1950, and so did natural gas, which is in purple. And funnily enough, so did cement. You might wonder about that. Well, in order to make cement, you take limestone, which is calcium carbonate, you burn it or heat it, and it gives off carbon dioxide, and you're left with calcium oxide, which is one of the bases for cement. So adding all these together, 90% of all the fossil fuel ever burned was burnt since 1950. That means within my lifetime, because I was born in 1942. So do we know where this carbon in the atmosphere came from? Yes, because we can use isotopes to tell us. So this graph goes from about 2005 on the right down to AD 1000 on the left. And again, we're looking mostly at ice core data, and the carbon dioxide scale is up the left-hand side. So all the little black squares and the lower part of the diagram are carbon dioxide measurements made in ice cores up until about early 19, just after 1850. And then we get into observations based on various observations. You see the carbon dioxide continues to increase. So how do we know where that carbon came from? Well, we can analyze the ratio of carbon 12 to carbon 13. And when we do that, we see that for the whole of this period from AD 1000 right up to about this 1850 green line, the carbon isotopic composition was fairly constant at about minus 6.5, the ratio. And then as we began burning fossil fuels, particularly coal, you see how the ratio started to decrease, and it got slowly went down as the carbon dioxide slowly went up. And then as the carbon dioxide steeply went up, the carbon isotopic composition dropped very rapidly and steeply down to minus 8.5. Now we know from the isotopic composition of the parent materials, the coal, we know where the coal came from, we know what its composition was, we know where the oil came from, we know where the natural gas came from, and we know what their isotopic compositions were. So we know what the isotopic composition of the fossil fuels has been through time and how it should have changed with all that burning. And this tells us that it is the burning of fossil fuel that has given rise to this isotopic signature, which tells us that it's carbon dioxide truly did come from burning fossil fuels. And different places burn different amounts. In the US, the amount of carbon burnt is 16.7, emissions is 16.7 tons per capita. China, 7.6. India, 1.6. In Europe, it's about 14. And in several of my lectures, I get people in the audience to say, they point at China and they say, see, it's the Chinese, you know, they're the ones doing all the problem. But what they forget is that starting around about 1980, with the deregulation promoted by Ronald Reagan and Margaret Thatcher, we began to offshore. The West began to offshore its manufacturing industry to places like China and Vietnam and Malaysia and Indonesia, where there was cheap labor and weak environmental regulation. In other words, we could carry on producing our stuff overseas. But most of that stuff that was made for us, and we re-imported it. So what we should be counting as part of our emissions is the stuff that we have imported from China that we sent to China to be made. And so in a sense, you could say, well, China isn't doing this for its own purposes, it's doing it for us. So when we count our carbon emissions, we actually need to multiply our own in-house carbon emissions from cars and houses by 3 in order to get the actual amount of emissions. And that's true of the United States, Western Europe, Australia, Canada, Britain, and so on. These are graphs that show the picture in a slightly different way. I want to start with the one on the right, the one with the blue coloration. This is the change in atmospheric CO2 concentration from 1750 right up to the present. And you can see this is parts per million per year. So you see very little change from 1750 right up till about 1950, really not a great deal of change in the rate of production, and a really steep increase from 1950 onwards. These other curves show you in the more geological context. You can see at the bottom, we see the rate of methane change in percent per year. And so for the whole of this past 20,000 years, you can see very little change, just occasional blips as we got into the deglaciation between 15,000 and 11,000 years ago, but then pretty flat right up until the past couple of hundred years. And then suddenly, whoops, it starts to take off. Similarly with carbon dioxide, which is the middle graph, almost no change for that whole 20,000 year period. And then suddenly, bang, right at the end, this massive jump. And that also ties in with the population change percent per year. Almost no change in the percent change per year from 11,700 years ago, right the way through, and then a really big kick up towards the end. So we're well aware that increasing population has a role to play in creating the Anthropocene. But we haven't only perturbed the carbon cycle, we've also perturbed the phosphorus cycle. This is part of us supplying fertilizers for farmers to use to produce the food we eat. So look at the top graph, and we're going from 1900 up through 1950, right up to the present. If you look at 1950, and you can see around about 1945, the world total began to really increase away from what it had been, and it ramped up. It went through a sort of flattish period between 1990 and 2005, and then since then it's ramped up again. And the problem with this is that farmers literally lard this stuff on their fields, spreading it widely, and as soon as it rains, an awful lot of that washes off, and it gets into the rivers and goes down to the sea. And when phosphate and nitrate from farm fields gets down to the ocean, these are nutrients, and so they feed on algae, and the algae eat up basically all the oxygen, and we're left with oceanic dead zones in places like the Gulf of Mexico, off New Orleans, in the Baltic, in the Black Sea, any enclosed sea or any area with a shallow coast with a big river is suffering these oceanic dead zones. And that's another signature that we would expect to see in the geological record in the future. We've also perturbed the nitrogen cycle. Here again, we're going back 20,000 years on the left, and we see an expanded view in this graph from the year 2005 right back to about 1850. But let's go to the left-hand side first, where we're dealing with Pleistocene and Holocene. And what you're looking at is two things. Green is the nitrogen isotope signal in the nitrate. And on the right, the blue scale is the actual nitrate concentration in parts per billion. And so we see that in blue, starting right on the far left, 20,000 years ago, it's jumped up and down and jumped up and down with an average of around about 80 parts per billion. And oops, sorry, that jumped a little bit too far, 80 parts per billion. And that's what it was around about 1850. And then it didn't change very much, but it started to really increase around about 1910 and 1920. And then since then, it shot up. It really shot up. We've been producing masses of this stuff to ladle onto farm fields. And you can see the way its composition has changed. Changing sources of this material through time meant that the nitrogen isotopic composition dropped through the Pleistocene down to about 10,000 years ago. And then it stayed fairly stable with the green dots just above the blue dots. And that was the way it was in about 1850. And it stayed that way till about 1910. And then you see, just as the blue signals started to rise up, the green signals started to fall down. This was in response to the what the red line is. That's the beginning of the industrial process created by these two Germans, Haber and Bosch, to process ammonia to produce nitrate for fertilizers. And so we're now dealing with artificial nitrogen in our fertilizers. In fact, I'll just go back to that one more time. In fact, that's roughly doubled the amount of reactive nitrogen at the Earth's surface. So this is another geological signal or geochemical signal that goes along with the phosphorus one. We can see this in ice cores and lake cores and sediment cores, as I've mentioned, dead zones. And for you yourselves, half the nitrogen in your bodies is now artificial from the Haber-Bosch process. So I want to look at now the perturbing of the hydrological cycle in the Anthropocene. So we're looking at the growth of dams. 1850 in the USA, those black dots show you where the dams were. 1900, not a lot of difference. 1950, an awful lot of dams, and that really then carried on massively, so that by 2000, you can hardly see any white on the right-hand side of the diagram. Every river in the United States, so every stream has been dammed 5, 6, or 7 times. The white areas are mostly mountains or deserts where you wouldn't have any dams anyway. So damming is a very important activity that we've done, and it changes the way that rivers carry silt to the sea, which has geological implications. So, but as well as considering what's happening to deltas, we also need to consider what's happening to sea level. And I think I already showed you the graph, yeah, I did, that shows that sea level's been rising for the past couple of hundred years. But here's the latest data from 1993, collected by a sequence of satellites, pink, blue, orange, and green. And so what I did was I drew a straight line through these with a ruler. That's this grayish blue line, the lower of the two lines. And then the dark blue line is the actual line that goes through the median of the data from the satellites. And you can clearly see that although these two lines followed each other up till about 2005, then there was a divergence. And by now in 2020, we're seeing a 2 centimeter, a 20 millimeter, 2 centimeter difference. So the rate of sea level rise is actually accelerating. The average rate for this whole period here is 3.3 millimeters per year. And the increase at the top right-hand end is taking it close to 4 millimeters per year. And that rate does seem to be increasing. So we're expecting sea level to increase with time. Now you might ask, why isn't sea level increasing at the same rate as temperature? And there's an easy answer to that. And the answer is, it takes quite a long time to melt ice. And the second answer is that sea level goes up because you heat water. But the amount of hot water in the ocean currently is focused near the surface. So over the top 700 meters. Gradually that heat is percolating down deeper and deeper into the ocean. And as that heat percolates, more of those deep waters will expand, and that will push sea level up further as well. So those two processes, ice melt and the percolation of heat into the ocean, both are causing sea level to rise, and causing it to rise slower than the rise in temperature. There's a lag in the system, and that lag could lead us to those high sea levels that I showed you at the beginning, which are typical of the Eemian. So what about deltas then? Well, deltas are because of all the damming, rivers are no longer taking sand and silt to the deltas to help them to sustain their level. And so they're sinking under their own weight. And what you see here, this is negative is upwards, right? So what we're seeing on the left-hand scale is a loss of 200, 400, 600, 800 millimeters. You can convert that into centimeters or meters. So these major rivers, the Chao Phraya, the Mississippi, the Ganges, Yangtze, and Mekong, just for example, are beginning to lose upwards of a meter, um, uh, a meter, yeah, getting on for a meter by now. And so the combination of the fact that the deltas are sinking and the sea level is rising means the deltas are getting a double whammy. And so the coastlines are retreating and the land's being flooded. And it's a big problem because deltas like the Mekong, for example, are the breadbasket for lots of Thailand and Vietnam. So they're going to lose their productive land that's giving them a food supply. We are also changing the Earth's surface. This is another part of the Anthropocene. On the left, you see a nice picture that looks full of plant life. Well, it's true. But once upon a time, this is Indonesia. Once upon a time, this picture would have been a tropical rainforest full of huge trees, all of them sucking carbon dioxide out of the atmosphere. They've all been chopped down and replaced by palm oil plants. So all of those little dots that you see in the picture, each of those is a separate palm oil plant. So they're absorbing far, far less carbon dioxide from the atmosphere than the original forest. And on the right-hand side, you see this graph which shows you what we're doing to our soils. And so the brown areas is where we have almost fully transformed our soils. And we've done that in three major ways. First of all, we nowadays use enormously heavy tractors, not like the small tractors that we used to use. They compress the soil, which is not very good for it. And the second thing is we plow deeper. Deep plowing actually turns up to the surface the organic matter that hosts carbon in the soil, and that organic matter decomposes and puts CO2 back into the atmosphere, and that helps to reduce the food potential for the roots of the plants. And then thirdly, we are larding these areas with fertilizer because the soils are moving towards becoming sterile. So we can manage it, but we're not doing very well with the soil. We need to think about ways of putting carbon back into the soil and improving its biodiversity. We have actually transformed more than 75% of the terrestrial biosphere by our agricultural and forestry processes and farming, beef and what have you. We're left with less than 25%, which is wildland. So that's another thing that's happening with the Anthropocene. What I'm trying to do here is to introduce to you the idea that we're not just talking about climate change, we're also talking in the Anthropocene about biodiversity change. The two are intimately linked. This set of pictures is merely meant to introduce you to the idea that, how we are transforming those land surfaces. Well, we're building on them. So we've got urban areas. These are big areas. This is all together. You add all these together and it adds up to 30 trillion tons, which is equivalent to about 50 kilograms per square meter of the planet. Rural housing, pasture land, croplands, trawling on the seafloor has a massive effect. All those lines you see on that middle picture represents where the otter boards that hold the trawl mouth apart have dug into the seabed, really uprooting the seabed ecology and transforming it. Pasture, the eroded soil on the right-hand middle diagram, chopping down trees for logging, usually leaves you with bare earth, and as soon as it rains, all that washes off and you're losing your topsoil. And then, of course, we put roads, we create plantations, which are not biologically diverse. They're monocultures. We create reservoirs, we create railways and so on. So we are changing the land surface. You can see that in London, for example, here in the lower map in red and yellow, what you're looking at is the thickness of the amount of soil and additions that we have made since World War II. So basically over the past 50 years. So anything that's red, for example, along the edges of the River Thames in that map, if you look across to the right-hand side to the legend, and you read that down, and the things in red are more than 5 or 6 or 10 or 15 meters and up to 15 or 30 meters thick. So enormous changes there. And the former rivers, you can see the line of the River Fleet has got lots of red color on it. And also the line of the River Walbrook has got lots of red color on it. Basically, in a sense, we filled in these rivers, valleys, in order to, make the land surface more level. So all of the red blobs that you see on this map represent quite considerable amounts of increasing the land surface. The yellow is areas where there's been very little change, as little as on the legends, as little as half a meter. And the top linear diagram there shows you the post-World War II thickness in gray over the pre-World War II its surface in red. So you can get an idea from the Tower of London on the right-hand side of the sorts of changes that have been made. And so these are, let's call these anthropogenic strata. They're extensive, they're mappable, we can date them from their technofossil content. I'll talk about technofossils in a minute. So in the Anthropocene, we have lots of new lithostratigraphic indicators. And one is aluminium, which is not found in nature. We are now producing aluminium at a rate of 35 million tons per year. And the other material is concrete, which we're now producing at a rate of 27 gigatons per year. So on the left-hand red scale is aluminium. You can see the aluminium curve in red. It amounts up to almost 500 million tons per year by the time we get to today, which is the right-hand side of the graph at the bottom. And concrete, similarly, that's the blue data. Those are not in millions of tons, they're in gigatons, which are billions of tons. And so you can see how the concrete's also increased. The annual concrete production is now just over 27 billion tons per year. And if we added together the total flux of all the sediments coming down the rivers, all the windblown dust, all the ice sheet contributions, all the glacier contributions, all the coastal erosion, that would be about the same amount. So we humans are having a huge, huge effect on the planet. If we took all that aluminium and we converted it into aluminium foil and spread it across the United States, we would completely cover the USA. Excuse me. On the right, you see a typical city. Awful lot of that is built with concrete. And it turns out that half the concrete ever produced has been produced in the past 20 years. And most of it's gone to building cities. And you could take all that concrete, and if you spread it across the planet, you'd have a layer which was about 1 kilogram per square meter across the planet. More novel lithostratigraphic indicators. By burning coal, we get fly ash. That little round thing in the top corner is a silica thing. It looks like pumice, doesn't it? With all those funny little air holes. And the scale bar shows you 20 microns. So these are really tiny little things. And they just go up in clouds of smoke like you see in the picture there. And they get distributed by the wind. And what we're interested in is how that's changed with time. So here we're going from 1830 on the left right up to 2010 on the right. And the different colors of the lines represent different areas like the UK and Ireland or Asia or North Africa. And you can see how initially from 1870 and so on, the amounts were fairly small. They started to rise slowly after about 1910. And then they underwent a very steep rise from 1950, which goes back to that first graph I showed you, where you could see that 90% of all the fossil fuels ever burnt have been burnt since 1950. And in burning the coal, we put lots of these spheroidal carbonaceous particles into the air. And you see that we started to get to a peak around about 1975. Why was that? Well, it's because countries became very worried by the fact they were getting more and more smog. The London smogs of 1952 were terrible. They killed lots of people, well over 1,000 or 2,000 people. And so gradually countries began to introduce Clean Air Acts to actually get this stuff out of the atmosphere. And so what we're seeing here with the decline to the right of 1980 is the decline in these things in the atmosphere because of Clean Air Acts. Now behind you see that gray shaded area, that's soot. which goes by the name of global black carbon. And so not surprisingly, soot has also increased to a peak, roughly the same amount, same time. Now, these two aerosols, the spheroidal carbonaceous particles and the soot, have different effects. These little carbonaceous particles, some of the aerosols like that tend to reflect solar energy, so that would lead to a cooling effect, whereas soot is completely black and absorbs heat, and so it leads actually to small amounts of global warming. What else have we been doing? Well, we've been producing lots of novel mineral and chemical indicators which we can find in the soil. So back in the 1700s, we were using carbon and calcium and iron. As we went to the 1800s, we started using other things like tungsten and tin and lead. 1900s, we were using lots of more things, copper and vanadium, nickel, molybdenum, thorium. And then when we get to the 2000s, goodness me, using a huge amount of different kinds of metals for things like catalytic converters in cars, for solar panels, for wind turbines, for computer chips and mobile phones. Altogether, we humans have produced something like 180,000 synthetic mineral-like substances, and many of which you'll find in your computer, or plastic, of course, is one of these, concrete's another one. And that compares with what nature has done. Over the past 4.5 billion years of the planet, nature has only produced 5,000 mineral-like substances. In addition to all that 180,000, we've produced 85,000 industrial chemicals, things like DDT, PCBs, and so on, which also get into the environment. And we can see these chemical signatures when we drill down, for example, extract cores from ice sheets, or in this case, a core from a Spanish lake. And we look at the lead here, and 3,000 years ago, we can see the signature from the Greeks and the Phoenicians, who were using mining and using a lot of lead. Then we have another peak around the AD 2000, where the Romans were using lead, and then we go to recent times, and that's from the lead used as an anti-knock additive in petrol, which we don't do anymore. So that is beginning to decline. One of our other chemical signatures that's everywhere is from atomic bomb tests in the atmosphere. So the gray bars in these two diagrams are the same. That's the number of atmospheric tests. When you have atmospheric tests, obviously this stuff goes just about everywhere. And so in the bottom diagram, you can see the blue line, that's the plutonium signal, which begins to die off as we get down. It's almost gone by the time we get to 1985. So it's a pretty much focused thing that starts just after 1950, is really peaks around about 1962. And one of the things that happened with atomic tests was that it changed the carbon-14 character of the atmosphere. So the green shows you the way in which the carbon-14 signal was also changed. That makes it hard to use carbon-14 for dating anything that's fairly recent. And one of the products that we quite frequently find in sediments, animals, and plants is cesium-137. And so here you see two things. First of all, the blue heavy line at the top, that's the signal at latitude 40 to 50 north, and which is where most of the tests took place. The dashed and dotted lines down here at lower levels represent the same signal of cesium, but at the northern latitudes of 60 to 70 degrees north, and more tropical latitudes of 20 to 30 degrees north. And the green stuff down at the bottom is their southern hemisphere equivalent. Obviously, a lot less in the southern hemisphere because most of the testing was done in the north. So again, this will help us to pin down the beginnings of Anthropocene time with the geochemical signature. Plastic is another new stratigraphic indicator for us. In 1950, we were producing, not we in the UK, but globally 1.7 million tons per year, and now it's up to 300 million tons per year. The annual production is equivalent to all of human biomass, so it's a lot. And cumulatively, it's something like 5 billion tons. If we turned it into plastic wrap, the sort you get in your kitchen, we could actually plastic wrap the whole of the planet. Plastic stratigraphy is an example of a piece of old plastic trapped in a Spanish beach, in a beach in, this is hardened beach sand, so they're already forming part of stratigraphy. And we find this stuff all over the oceans, which means it's also getting into ocean sediments. And the reason for that, in the map at the bottom, you can see these arrows represent the way in which the major ocean gyres rotate. And in their rotation, what tends to happen is the plastic at the surface tends to be washed into the middle of these things. So on the left in the Pacific, that orange blob is the Great North Pacific garbage patch, which people are trying to clear up. In the North Atlantic, that orange blob is the accumulation of this stuff in what we call the Sargasso Sea. So what does it comprise? Well, up at the top right, you see the scale bar there is 1 millimeter. So these are fibers, these are plastic fibers found in sediments from Lake Ontario in the middle. There's the familiar picture that you often see of plastic bottles washed up on the seashore somewhere. And here, this is on the left, is the Spanish continental margin, 1,000 meters deep. And all of that wiry looking stuff is actually a huge fishing nets that have been discarded and are just lying around on the bottom to become incorporated into sediment. The problem with a lot of this plastic is that in the ocean, it degrades into very small particles, and those get into animals. Fish eat them. And we then eat the fish. So we're actually eating some of this plastic. Microplastics are a problem, not just from the decay of plastics, but also because we put tiny bits into the environment. So we put these, every time you wash a fleece, 100,000 of these little particles comes off into the wash, and these fibers go down the drain and into the ocean. And on the right are what companies used to do is produce cleaning products that contain little tiny microplastic beads that would roughen your skin and help you to slough off the dead skin cells. And now, because of environmental pressure, we're not supposed to do that anymore. And I hope that companies are no longer including those. We can use technofossils instead of biological fossils because manufacturers are always changing their products with time. It turns out that even the humble clothes peg down at the bottom right has changed its shape and its color and the way it's manufactured over time. Next to it is the humble paperclip that's also changed with time. And we know when these changes took place quite precisely. Going across to the bottom left, furniture gets discarded. It also has changed with time. Even the humble nut and bolt has changed with time, the materials in it and the shapes. Moving up above that, you see the way mobile phones have changed. At the top of that line of mobile phones is a thing the size of a house brick, which you used to have to hold up to your ear, and going down to very tiny, more modern phones. And then here next to that is all the different kinds of plastics. On the far right is clothing. Clothing has changed. We know when clothing changed. Above that are ballpoint pens, next to them toothbrushes. The designs of these things are constantly changing. And because we know when those designs changed, we can actually, if we find these buried in landfill, we can date the landfill. Similarly, even things like cutlery changes with time. We've also been perturbing biodiversity with colonization. We transplanted loads and loads and loads of animals and plants from one area to another. In effect, they operate as invasive species. So looking at this list is just a typical list, not a comprehensive one. New Zealand plants, number of native species 1790, number of invasives almost the same, 1570. Go to Hawaii, very similar picture. Go down to Tristan da Cunha, there are more invasives, 97, than there are natives. Go to South Georgia, 54 to 26, more invasives than natives. Southern Africa, freshwater fish. Again, lots of introduced species, invasives, not as many as the native ones. California freshwater fish, and so on. So the story goes on. So where we go to see the way the biology has changed down the geological column in the Anthropocene, these are things that we would look for. Here's another example of what our shipping does. If you imagine you're a shipmaster and you're in Russia or the Ukraine, and you get an order from Canada to bring stuff to come and pick up a load in the Great Lakes area, right? So in order to get your ship balanced, you pump in ballast water from your surroundings, and it will be full of larvae. Particularly annoying are the larvae of the zebra mussel, because by the time you get to the Great Lakes to take on your load, you have to discharge your ballast water. So you discharge it into the Great Lakes, and it gets into the streams and rivers around the Great Lakes. And these are now all full of zebra mussels, which outcompete all the local ones. They block channels, they block tubes getting fresh water from the river. They're really a huge nuisance. And so these sort of invasions are a big problem. Extinction too is a problem, another biodiversity challenge. Go back on this graph to 1500 to 1600, we can see already that mammals were being exploited, wild mammals. That's not too surprising. I mean, even prehistoric man was trying to hunt big animals because you got more meat on the hoof to take home to feed your kids. So gradually over time, even since 1500, there were rather small increases because the global population wasn't changing very fast. But as global population began to rise, and more of these animals and birds and vertebrates started to be lost, as did fish and reptiles and amphibians. So right now in the 1900s to 2010s, the extinction rate is very much higher than it was back in the 1500s. Now the dashed line at the bottom, the black dashed line, is the background rate of 2 extinctions per million species years. And so what you can see is we are now seeing extinctions that are much faster than the natural background rate. Now, the WWF, the Worldwide Fund for Nature, did a report in 2018, a global report, which showed that mammals and birds and fish and reptile populations have fallen on average by 60% just since 1970. So there's something serious going on, which is changing our biodiversity, and that would be obvious in future to future geologists looking back into the record. If we go back in time, what we can see is from the diagram at the top right, where you see the picture of the mammoth, this box represents the size of the pre-human terrestrial vertebrate biomass. The little box next to it with the picture of the elephant is today's vertebrate wildlife, which is about 1/4 of what it was in pre-human times. So already we have lost an awful lot of our vertebrate wildlife. To the left of that is humans. So humans proportion of the terrestrial biomass is now about double what the pre-human terrestrial vertebrate biomass was. So we've already gone further in producing biomass than there was on the planet before we were around. And we have grown our own domesticated animals to feed us as pigs, sheep, horses, dogs, cats, chickens, all of those added up. And that's not quite double the human biomass, but it's about 1.5 times the human biomass. And you add these together, and there are far more large animals on the planet now that are not naturally running around back in pre-human times. So if you look at it another way, you could say, right, we know there are 200,000 wolves on the planet, but there are also 400 million dogs. We know there are just 40,000 lions left, but there are 600 million cats. In Africa, there are 900,000 African buffaloes, but globally, there are 1.5 billion cows. And we know there are 50 million penguins, but there are 20 billion chickens. And it looks as if for our descendants, geologist descendants, the likeliest future fossils that they're going to find are going to be chicken bones. Let's think about forests for a moment. On the left is a nice picture of a Canadian boreal forest, nice and healthy. On the right is a very similar forest, also in Canada, which has been stripped. And it's been stripped by something called the pine bark beetle. You can see the way the bark's falling off. And this is because the warming, as it's going on in the north, and we should, by the way, we should all remember that when you're told that the global average warming is 1.2 degrees centigrade, what that means for the Arctic is it's at least double that. It's probably 2.4 or 3 degrees or 4 degrees of warming in the Arctic. And that's because they're losing ice. So the ice is no longer reflecting heat, reflecting the sun's heat. That heat is actually warming the ocean. So what happens is that the insects, like these pine bark beetles, now can reproduce twice per year instead of once per year. And the poor old trees aren't used to having 2 invasions of this insect per year. So they're, giving up the ghost. What about future changes? Well, we can imagine a situation in which warming actually gets rid of the Amazon rainforest on the left and replaces it with savanna, which we see on the right. We all like coral reefs, I'm sure, and the popular picture of a coral reef is the one on the left. On the right, we see a coral reef devastated not by ocean acidification, but by coral bleaching from warm temperatures. That's increasing around the world. But also any organism that makes its skeleton out of calcium carbonate, like corals, is at risk in the ocean today because of ocean acidification. This is a byproduct of us putting carbon emissions into the atmosphere. When you put CO2 into the atmosphere, that carbon dioxide has to balance with what's in the ocean. The ocean and the atmosphere have to be in chemical equilibrium. And so CO2 that we put into the atmosphere then mixes into the ocean. And when it gets into the ocean, that chemically makes the ocean very slightly more acid, and in fact by about 30% at the moment. And that affects the ability of organisms that build calcium carbonate skeletons to do that. So let me conclude then. I'm sure you've heard enough from me at the moment. The Anthropocene is real. Whether we can get the International Commission to agree with us remains to be seen. But right now we're operating it as if it is real. The Anthropocene units that we have are thin and young and discontinuous, but they're also global. We can see they've got distinct physical, chemical, and biological signals. The key signals are larger than those in the Holocene, for example, carbon dioxide, methane, carbon-13, or those signals are entirely novel, like aluminium, plutonium, concrete, plastic, and fly ash, none of which were around in the Holocene. The changes that we're seeing are obviously going to be long-lived, and many of them are irreversible. And the trends are continuing. Warming is continuing, sea level rise is continuing, invasive species from one region to another is continuing, extinctions are continuing. So we can see these changes are going to get bigger with time as we go on. Some of the signals have yet to breach the Holocene conditions. Temperature has already gone above the heights of the early Holocene climate optimum, but sea level is not there yet, and for a reason that I explained to you earlier, which is that it's taking time for heat to penetrate deep enough into the ocean to raise sea level from that perspective, and also because the ice is melting slowly, and so it's lagging the temperature rise, but we're moving in the right direction, or moving in that direction. So the question is, well, what kind of Anthropocene do you want? Now, this final slide is, I always like to end with a message of hope. And because people often ask me when I give lectures, well, what can we do about this? Well, there's a lot of things you can do. Most of what needs to be done has to be done by government or by industry or by government and industry, but individuals are important. You can demand change. You can vote for what you want. You can write or phone or meet with your MP and pressure them. or your local councils. You can demand the government puts more green-related R&D. You can demand subsidies for green power. This is if you feel that you really want to go in that direction. There might be some who work in the fossil fuel industry who don't want to follow this particular path, but this is the path that governments globally are currently following. So if you believe that's the way to go, you can demand faster builds of the new infrastructure for solar and wind and nuclear. You can influence the market, try to eat less meat. There are now plant-based alternatives which are just as tasty. What sort of car do you drive? Can you buy an electric vehicle? Can you buy a hybrid vehicle? Are you driving an SUV? SUVs are interesting, aren't they? I mean, people love SUVs. Yes, they're big and they're solid. Oh, yes, and your neighbor's got one, so you've got to have one too. But if it's a petrol one or a diesel one, they emit 25% more emissions than your neighbor's standard family car. And the other thing about them is they use an awful lot more carbon dioxide emissions in order to make them. Just think about the size of the tires. Think the width of the tire on an SUV is about double what it is on a standard family car. The weight of an SUV is almost double what a standard family car is. And all of that material has to come from somewhere and be made. And in the manufacture of those things, it's actually creating many more emissions. If you have your electricity supplier is not green, you can change to a green one. This is a really hot topic at the moment because of the problems with the supply of natural gas. So I won't talk about that anymore. But if you own a home, you can do something about your home's emissions. You may be losing lots of heat through your roof. You perhaps could install solar panels. You could install heat pumps. Heat pumps keep your house warmer in the winter and cooler in the summer, so they actually save on energy. Investment wise, you can change to a green pension fund. You can invest in green shares. You can actually buy green bonds, I think, these days. And you can demand the maximizing of recycling. Not recycling is encouraging waste. Waste means that you're producing emissions, more emissions than you need. Okay, and that funny looking picture is very dim, but you can possibly see in the background, those are the wind farms. That's the wind farm off Shoreham, which I photographed the other day, and I couldn't get it on a clear day. So there we are, the end. I hope you found that useful. And if you have any questions, I'd be glad to entertain them. Oh, what happened there? Zoom, go back.
Thank you very much, Colin. That was very interesting. It's a little bit depressing from my point of view, but I think those messages of what we can do about it are also very good. I think there's probably one you could add to that slide actually in terms of actually reduce waste so you don't have to do as much recycling, not use as many things. I think that's something that would be really good to have on there. If anyone's got any questions, could you pop them in the chat box? I think, Peter, you've been very keen and you've already put in a couple of comments about the timeline that we're working to at the moment in terms of, it looks like we do need to act quickly to get this over. I think, can you see the chat?
Yeah, hi, I did put some in the chat. Hi, Colin. I mean, I really enjoyed your talk. Shame there's only about 20 people listening to it, but inshallah. I could have heard this talk from any green activist to an extent. And what you have not made the case for, in my opinion, is defining a new geologic epoch, or whatever the technical term is, the Anthropocene. There is a degree of, I've always felt a bit ambivalent about the Anthropocene stuff, because are we getting ahead of ourselves? Because, you know, Boris Johnson is going to go and save the world in November. Well, possibly not. But 100 years time, 20 years time, we might get things over and get stuff sorted back. I just wonder, if you move forward a million years, will this just look to be a little peak of activity to future geologists, a bit like the Pleistocene thermal maximum, for instance? So I'm kind of a little bit ambivalent about, are we slightly arrogant, a bit egotistic in trying to say, right, we have set up a new era. You know, we haven't had meteorite impact, we haven't had major volcanic events, we haven't had all the things which we can use to define previous changes in the geological story. That's my point, I think.
Yeah, well, I think you're absolutely right. You know, I mean, what we're trying to do is to make a case, and you know, when you give one of these lectures, you can't get all the points across in time. But that's why when I started off, you may not have been around when I started it off, but we produced this Cambridge University Press book in 2019, which spells out the case in some considerable detail. So the evidence that we are using at the moment is all summarized in that book. So if you want to get a more detailed view of the Anthropocene, that would be a good place to start. But as I said at the beginning, one of our primary tasks now is to actually produce the evidence that there is a boundary that we can recognize globally, and with that recognition, we would hope to cement the case for saying, yeah, there is an event horizon here which shows that there is a considerable change taking place. And when you see these considerable changes in the geological record, some of them do become accepted as new epochs. So it's a question that ultimately the International Commission on Stratigraphy is going to have to answer. And one of their questions will be, is this going to be enough to be an epoch? Or is it like the Paleocene, Eocene, climatic, no, Paleocene, Eocene thermal maximum, the PETM? Is it going to be just an event? So you're right to raise that point.
Yeah, but I mean, I'm going to go quite well. You haven't actually answered my question, to be honest. I understand why you're doing it, and I can see the validity for doing it if you want, but you haven't actually answered the question, do we need to do it? And that's always been my concern from the very early papers on the Anthropocene. Do we actually need to be doing it at the moment?
Well, obviously, those of us on the committee working on this think that we do. And the book is what makes the case that we have up until now. So I'm going to have to repeat and say, well, you know, we've actually made quite a good case. And if you want to really get into the nitty-gritty and question it, then go ahead and read the book. You might find it entertaining or interesting even.
We've got another question from David. He says, thanks, most thought-provoking. Rather than reducing something, what do we stop doing? Stopping would have much greater impact than reducing.
Yes. Well, of course, right now, the governments around the world are asking us to stop putting carbon dioxide into the atmosphere. And the idea is that that will help to reduce carbon dioxide levels, but it won't be enough. We will actually have to take carbon out of the atmosphere in using some process like direct air capture and carbon capture and storage, DACS for short. So the idea there is that this is something being developed at the University of Arizona by Klaus Lackner, where you have an array of fans that blasts air over catalyst with a chemical that actually absorbs the carbon dioxide. And you then have to find a way to get rid of the carbon dioxide that you've captured or store it. And so there's a huge amount of discussion about how that can be done, how it can be scaled up to industrial level, what it would cost. And, you know, until we see those sorts of figures, it's really difficult to judge quite how that will work. But the idea is to get this kind of technology going within the next 20 years. So it's this 20-year period in front of us is the period where we're going to have to really get to grips with stopping emissions, and then further than that, taking carbon out of the atmosphere to reduce the carbon dioxide levels to levels that will not warm the planet to the point where sea level rises by those Eemian levels of plus 15 meters.
I think if anyone else has got any other questions, now time to quickly raise them before we close. Carol said, thank you. It's a very thought-provoking presentation, comprehensive and fascinating, and very thought-provoking. Many thanks. It's always good. I think I have to reiterate that. It was a very good talk. I think I've just got a quick little sort of thought question. Obviously, at the start of your presentation, you were presenting those golden markers showing the different deviations. Just as sort of a thought piece, in 10,000 years, what do you think would be like the really key one that you can see now that people would turn around and go, yep, that would be the start?
Well, you're still going to see the plutonium signal in 10,000 years.
Yeah. So you think that's one that will stand out the most? Yeah,
and that's a key marker for, basically a key marker for the base of the Anthropocene, because it peaks in about 1960, so it's very close to the 1950 boundary.
I think we've got a question from Catherine. Super whistle-stop snapshot tour of all the main changes happening and accelerating, probably down to human interference, particularly in the last 50 years. Really appreciate you presenting this. Hope many more viewers get to view the recording. What questions are you moving? If more watch this, then maybe more would change their attitudes. What we need is less green materials. And I think everyone else is just saying thank you. So I think we're probably getting to that point where we can close.
Good.
So yes, that was very good. Thank you very much, Colin.
You're very welcome.
And as I said, I think we've been recording it, so we can circulate that later on if people have missed it. I know we've got 1 or 2 people that said they couldn't make it tonight, and they're quite keen to see the recording, which is good.
Do you get feedback from those?
From the recordings?
Yeah.
Not the regional group, but I'll ask the Geological if they ever get any questions. As it's on a YouTube page, there may be comments being logged or reviews as video. I'll double check for you.
Okay, thank you very much.
I'll send you a link when it's been uploaded as well, so you can keep a track of it. It'll be good.
That's good, thank you.
Before everyone goes, just a reminder of our next talk, which kind of ties in quite nicely with this one. It'll be on the 13th of October by David Boone from the BGS, and it's talking about geoenergy observatories, characterizing the subsurface to support the transition to a low carbon economy. So that'll be talking about 2 key case studies, looking at Cardiff open loop heat pumps in an urban geo observatory down there, and the UK Geo-Glasgow project looking at mine water energy. So that'll be probably an interesting follow-up to this one.
Very good.
Well, thank you very much, everyone. And thank you once again, Colin. That was an excellent talk. And I hope to see you all at the next meeting.
Thank you. Thank you, Colin. That was great.
Thanks. Okay,
Bye-bye.
thanks. Bye.